Hello students, I am Dr. Sumit Majumdar. I am a pass out of IIT-JEE. I am from the 2003 batch. Since then, I am with askIITians. We have already been discussing quite a few chapters from the class 12 syllabus. Now, here is another one. This is moving charges and magnetism. So what basically do we need to understand about it? We see magnets everywhere. It actually exists everywhere around us. So let's try to understand more about magnetism. Hello students. Let's first start off with the moving charges and magnetism. So when we talk about the moving charges and magnetism, so what is the first thing that comes to your mind? When you have any particular charge, any charge is not going to be at rest, right? Because the charges do not have very high mass. All the charges will continue to be in motion. So generally, when we are talking about the motion of the charges are going to be in a circular path. For instance, if we talk about the case of the motion of an electron, about an atom, about the nucleus of an atom, so there again the motion is circular. Or you can also say if there is a perpendicular field that is acting, that is going to result into a kind of a helical path. Right? So let's try to understand about what exactly are the types of motion that is produced in the presence of a magnetic field. So let's give a brief breakup of what all are the things that we are going to discuss here. First of all, we'll understand about the solenoid and the toroid, what is the difference between them. Then we'll also try to understand about what exactly is the force that acts between two current carrying conductors when the current is moving in the same direction. Because when you have the current moving in the same direction, you have the force being attractive, and when the current is moving in opposite directions in the parallel wires, that case the force is going to be repulsive. We'll be using the right hand rule for finding out the directions. Then moving on, we talk about the Ampere law. So the Ampere's current law, and that results into a torque on the current loop and also produces a magnetic dipole. Going further, what we talk about the rectangular current loop, the circular current loop as a magnetic dipole, the magnetic dipole moment of a revolving electron. Basically, when an electron revolves, obviously it's going to be revolving about the center of the atom. So if it is revolving about the center is going to be positively charged. Right? So that results into a kind of a dipole. You have a positive center and you have a negative center. So there is a distance between the positive center, which is the nucleus, and the negative, that is the electron. The total number of electrons that are there is going to be equals to the charge of the positive charge as well, positive nucleus as well. Therefore, that results into a kind of a dipole. That is what we understand about the magnetic dipole moment of a revolving electron. First of all, when we say that we have to understand about the magnetic field at the center of a current carrying loop. So how do we understand about this? For instance, if you try to consider about this current carrying loop, so here you have this loop, the current is coming in from here, moving in this circular path and then coming out, right? So this results into what is a kind of current flow. Further, at any place like here, the current direction, which is going to be tangential, is going to be perpendicular to the radius. So the current is going to be moving perpendicularly. But you know that current is not a vector quantity. So what we say, we associate a current element, that is how much is the current flowing in a very small part of this particular ring. So that is what is known as a current element. So IDL represents the current element, and that is perpendicular to the radial vector. Okay, so IDL is the current element which is perpendicular to the radial vector, and we've tried to find out the product of the current element and the radius at different instants of time. So this is how the current is going to be flowing. Now, if we talk about this, the direction of DL, as you can see, is along the tangent. So this is the direction of the DL that we have. Okay, now since the DL is going to be perpendicular to R, so from the Biot-Savart law, the magnetic field at the center, the magnetic field at this particular point O is going to be given by this. That is, you take a very small current element here, you take a very small part here which has a length dl, and since the current is flowing through it, so current is going to be continuous, it's going to be a constant value, and therefore idl is the current element here, And then if you try to take any particular component, here is obviously the current element is making an angle r, is making an angle 90 degree with r. Therefore, ideal sine 90 is what we have divided by r square. So if we try to simplify this, so we'll get mu naught divided by 4 pi ideal over r square. So this is the amount of magnetic field that is produced. Going further, if we try to understand how exactly the magnetic field at the center of a current carrying loop has to be figured out. So what we are trying to do, as we took a very small current element, so we now have to integrate over all possible such elements. So what we have tried to do here, if we try to see it, so you can see that the current element, if you try to take a component here, so there is going to be a magnetic field component that's going to be varying. So since it's a uniformly circular ring, so therefore the current element that's going to be resulting is also going to be moving. So there is a tangential component part here, and this is nothing but the magnetic field component. So that is what we get by an integration, you can say, because we know that at any particular point the magnetic field is going to be given by the Biot-Savart law, which is nothing but mu naught by 4 pi ideal sine theta over r square. Sine theta here is going to be 1 because the angle theta is equal to 90 degrees. So if we are going to integrate this, so this results into something like this. Now when you are integrating over dl, what is dl? dl was a very small part. Therefore, if you integrate over the total circumference, so how much is going to be the total length? So the total length here is going to be equal to 2 pi r. So this is nothing but the circumference, which is equal to 2 pi r. Because the current element I is constant, mu naught is a constant, the radius r that you have here, that is a constant. Therefore, these factors can be taken out. So if you just find it out, so this is what we get. So here is just a small correction here. This should not be mu naught m naught. This is nothing but mu naught. This is what we get. Now the directions. What are going to be the directions of current? So this results into what are known as the magnetic field lines. So if the current is flowing like this, then the magnetic field lines are going to be going like this, or vice versa. Please understand, all of these are perpendicular to each other. In the case of a magnetic field, the way the current and the charges are going to be moving, that is the velocity, the way the force is going to be acting, and the magnetic field produced. All these things are going to be mutually perpendicular. That is the force, the velocity, and the magnetic field. So these three are the things that are going to be always perpendicular. Okay. Using this, since you already know about all those things, I'm not going to go into much detail about it. So here, let's try to understand it. It says a charged particle moving in a uniform magnetic field, okay, and it loses 4% of its kinetic energy. So if it loses 4% of its kinetic energy, so how exactly we are going to do it? You know that because it is in motion always, so what exactly will we get? If we just do it QVB and sine theta, so this is the Lorentz force that we have. This is going to be responsible for the centripetal path or centripetal force, right? Assuming that the velocity and the magnetic field are perpendicular to each other, so we can safely say sine theta is equal to 1. Therefore, we can say mv square is nothing but qvb into r. Now, its kinetic energy. So, what is going to be its kinetic energy? We can simply say half mv square is equal to half of qvb into r. So, what is changing? So, this is the factor of kinetic energy. Therefore, if there is any change in the kinetic energy, then how much is going to be the radius of curvature? So, let's try to figure it out. So, what we can do simply, if you just do a simple error analysis, so you will find that the change in kinetic energy over the original kinetic energy is going to be equals to it's going to be equals to twice of the change in the radius over the original radius. Okay. So if you do this, so since the kinetic energy changes by 4%, therefore the change in the radius of curvature is going to be half of it, that is equal to 2%. This can easily be seen because this whole factor has a means this is given by the kinetic energy, and there is a factor of half. So that's the reason the change in radius is going to be coming from this particular value. So it should be half of it. It cannot be the same. Okay. Moving on to the next question. We have two charged particles, each of mass m and charge q, are projected in a uniform magnetic field B with the same speed as such that the planes of motion of particles are perpendicular to the magnetic field B. Okay. Now when you are projecting two circular particles, each of them with a mass m, and they are projected in a uniform magnetic field B, right, with the same speed. So if you are doing that, in that case, what is going to happen? What are the forces that are going to be acting? Both of them are going to be acted upon, even though they are projected along different directions. It doesn't matter, as long as they are being acted upon by the same magnetic field and the magnetic field is perpendicular to their plane of motion. That means both of them would be acted upon by the same amount of force. And if they are being acted upon by the same amount of force, then they are going to be moving in a helical path, or since there is no electric field present, so they will be moving in a circular path. So since the QV and B are perpendicular to each other, so the net force that is going to be acting is going to be given by the cross product, and since that is going to be given by the cross product results into a circular path. Since you get a circular path, so irrespective of their directions being different, they are going to be moving on the circular path and they have the same mass and the same charge. Therefore, the radius also is going to be the same. Okay, further. This says if the current is flowing towards you, current is flowing in a clockwise direction in a circular coil, the direction of lines of force inside the coil is. So if you use the right hand rule, what exactly do you get? The current is flowing in a clockwise manner, right? So if you take either of this, so let's say this represents the direction of current, either of it, please understand, these should be mutually perpendicular to each other. That should be it. So here, if I say that this represents the current, this represents the velocity, the length of the path, and this represents the force. So if you have this, the current is moving like this, correct? The current is moving like this, and therefore what is going to happen? The force, how exactly is the force going to be changing? Because the magnetic field has to be constant, correct? So if the magnetic field has to be constant, the magnetic field should not be changing. The direction of the magnetic field should not be changing. So if the magnetic field is not changing, in that case it should always be directed towards the center. Okay, so the magnetic field is not changing, so that is along a perpendicular direction. The current is tangential, so what are you left with? You are always going to be left with the force. Force is going to be resulting in towards the center. The body or the charged particle is going to be moving towards the center, which is going to be responsible for the centripetal path, and therefore the direction of force lines are going to be acted upon towards the center. This is very much simple, you don't have to actually do it, you can just visualize this. Hopefully you understood till this point. Stay tuned for the next part. So students, we learned about magnetism, how actually when any electron moves about an atom or within an atom, how exactly it produces a magnetic field. We can generalize that for the case of an electron, or for that matter any current flowing in a circular loop that results into what is known as a Biot-Savart's law. We generalized it and found that what exactly are the types of examples that can be held or that can be understood with the help of a Biot-Savart's law. Now, this was all about the introduction of magnetism. Let's now go further and try to understand about what exactly is a magnet. So that we are going to discuss in our next part, that is magnetic dipole. So stay tuned for that.